Welcome to week 5 of our course, Boltzmann Law, Physics to Computing. This is the first lecture for this week, which is the last week of this course. Now, as you know, last week we set up this general framework for discussing quantum spins of how you write the energy matrix, the density matrix, and deduce the expectation values of observables. Now, and we did it by kind of extending the concepts from the classical spins, which we had introduced in weeks 2 and 3. Now, in that context, if you remember, the classical spins, the idea came very early in this course, like in lecture 1.2, I believe, where we introduced this classical Boltzmann law by saying that the system is connected to a reservoir, and this law reflects the properties of the reservoir. Now, of course, when translating to quantum, we didn't have to bring up all those deep thoughts. We just went from the energy function to this energy matrix. But of course, the physical picture is still the same, that it involves these interactions with the reservoir which keeps it in equilibrium. Now, in general, if we had to start from this system plus reservoirs, this whole thing, then what would happen is we'd actually have a density matrix that would also involve the reservoir states. So you'd have reservoir being in state 1, state 2, state 3, and of course enormous number, because reservoirs are usually huge things with many degrees of freedom. So these would be huge matrices, and there would be all these rho ij, a density matrix for our system corresponding to each of these reservoir states. And the density matrix that we've been calculating is kind of like the sum of all these, as if you took all the diagonal elements. Right? This is the density matrix if the reservoir is in state 1. This is the density matrix if it is in state 2, and so on. And what we are working with is kind of a sum of all of those with the right probabilities. And it all comes out naturally in our calculations for the equilibrium case, because we are using this framework that we inherited from classical statistical mechanics. Now, if on the other hand we were dealing with an isolated system, then you see we'd be looking at only one of the terms here. And in that case, you can write the density matrix as a product of what's called a wave function. So rho ij is like psi I, psi j complex conjugate. And this is much simpler, of course, because rho ij is a matrix, whereas this is a column vector. See? But in general, when you're trying to discuss an open system, you see, we have a sum over all the reservoir states. And in that case, the rho ij we get cannot be simply factorized this way, which is why you really need the density matrix. And that's what we had been doing all of last week. But if you have an isolated system, then you could write it this way, which means the density matrix can be written as the product of a column vector and a row vector. So it's like if I want rho ij, that's the ith row and the jth column, I take psi I and multiply it by psi j star. That would be the ijth element of rho, which in matrix notation you could write as rho equals psi psi dagger, because this psi, this is the column vector, and psi dagger is this row vector, and when you multiply them, you get a matrix. So this n by 1 and 1 by n, when you multiply it, you get a matrix that's n by n. And n, of course, is the total number of configurations, which is 2 to the power small n, which is the number of bits that we had talked about. But the main point then is that so far we have been talking about this quantum systems in equilibrium, right? That's the density matrix e to the power minus h. What that tells you is what the situation is in equilibrium, and equilibrium is attained because it is connected to a reservoir. But going forwards this week, we'll be talking more about an isolated system, you see, and how it evolves in time. And in that case, you can talk in terms of the wave function, which is simpler because it's got just n components, whereas the matrix has n squared components. Okay? But when reservoirs are involved, you cannot have this factorization, which is why we haven't talked about wave functions last week. Now, just to drive home this point a little more, let's look at one of the results we had from, I believe this was the second lecture of last week, 4.2, where we calculated the equilibrium density matrix if you had a H that was pointing in the along theta. Now, we calculated the density matrix. Now, if you assume theta equals 0, that means that this bias term is all in the z direction, and you put a large H. Then what happens is theta equals 0, so off diagonal goes away. Cosine theta is 1, tan hyperbolic H is 1, and so you get this matrix. Now, this would be the density matrix in this condition. Now, can you factorize it? Yes. You see, you can easily write this as 0, 1 times 0, 1. If you can check this out. When you multiply it, you'll get this matrix. So what that means is this is the wave function. So you can write rho as psi psi dagger. And you could interpret it by saying, oh, I see. So it means that this quantum spin is all in the -1 state. It's all in this -1 state, it's pointing downwards. And that makes sense because you're putting a large bias term in the z direction, which means that if this were to point upwards, it would have a very big energy, and so it wants to point downwards. It goes to the lowest one. Okay. Now, what if you put a large H at 180 degrees in the opposite direction? That's theta equals pi. Well, in that case, cosine theta is -1, tan hyperbolic H is still 1. So now you get a +1 here, and the rest are 0. Can this be factorized? Yes. You could write it as a product of 1, 0, 1, 0. That's again psi psi dagger. And what this wave function shows you is that the spin is all in the +1 direction. And that corresponds to the spin pointing upwards. So if you put a big H pointing downwards, the spin will point upwards. And incidentally, I should mention that in a lot of the literature, people define the H with a minus sign here. And so it may not, the conclusions we are coming to could be the exact opposite of what you might see in some of the literature. This is just to warn you if you're trying to correlate this with what you might see elsewhere. But the basic point, I think, is the same. It's just the convention of whether you define H as minus H dot sigma or plus H dot sigma. Okay. Anyway, but the main point here is that when you get into one of these pure states, you can easily factorize. What if I put a H in the x direction, large H in the x direction? Now it looks more complicated because now you see cosine pi over 2 is 0. So cosine theta is 0. So the diagonal elements is 1 minus 0, which becomes +1. But the off diagonal terms are now not 0 because sine theta is 1 and tan hyperbolic H is 1. So it's -1, -1. Now, can this be factorized? And the answer is yes. Actually, you could write it as +1 -1, +1 -1. And if you multiply this out, you'll get that. So again, you can interpret this as the wave function. So what that means is the wave function tells you that the probability of being up or down is equal. You see, it's +1. Remember one thing, there's a half here, so I should have a 1 over √2 multiplying each one of these, which I have left out. Okay, just for clarity I left that out, but otherwise these amplitudes are really 1 over √2, so that when you square it you get half. Okay. But the important point I wanted to make is that this actually represents a spin in the negative x direction. That you might expect because you're putting a big H in the positive x, and so the spin now goes to the negative x. But a negative x is actually a superposition of up and down. So it's like up has a component +1, down has a -1. So it's like up, and so it's like a spin pointing to the quantum spin pointing to the left is like up minus down, right? And this is a little bit like vectors. It's just that the angles are kind of twice. So in vectors, you have seen that when you have a vector pointing at 45 degrees, you can think of it as a superposition of a vertical vector and a horizontal vector. So when you talk of spinors, the thing is what used to be 45 degrees for vectors becomes 90 degrees for spinors. So it's a superposition of something at 90 degrees and of components that are at 90 degrees to the original. Yeah. Now let us look at a case where it cannot be factorized. Supposing h equals 0. Now you see the system can be up or down because they both have the same energy, because h is 0, so all possibilities have the same energy. So now when you calculate the density matrix with h equal to 0, you get this 1, 1, 0, 0. And the thing is, you can try this out, you cannot write it as psi dagger. But what you can do is think of it as if it has got two terms. One is this and the other is this. And it's half of this plus half of this. So it is like 50%. There's a 50% probability of looking like this, a 50% probability of looking like this. That's what this density matrix represents. So there is no unique wave function in this case. It could be this or this. You can say, well, couldn't I have just added these two wave functions? This is psi dagger. So I could say 50% psi plus 50% this. Well, no, because then you'd get +1. When I add these two, I'd get +1, +1. And that would actually correspond to a spin pointing in the x direction. So the point to note is, when you have a density matrix looking like this, the wave function is this. But when you have a density matrix like this, there's no unique wave function. It's like 50% of one and 50% of the other. This represents what you might call an unpolarized collection of electrons. It could be up or down 50-50. This is an x-polarized collection. And those are not the same thing. Just as unpolarized light is not the same as 45-degree polarized light. Same with electrons. So to recap, what we've been saying then is what we talked about last week is based on this equilibrium density matrix, you see, and all of adiabatic quantum computing is based on these equilibrium systems. You engineer a quantum system, let it go to equilibrium, and that's what gives you the solutions that you want. That's how adiabatic quantum computing works. This week we'll be talking about gated quantum computing, where we're thinking in terms of an isolated system. And for an isolated system, the density matrix can be factorized, and we can talk in terms of the wave function. And that's simpler because instead of n squared elements, we are now dealing with just n elements. In terms of predicting observations, well, same story. We had the general rule here. Now what we can do is, instead of rho, we can put psi dagger. And of course, when you take trace of product of A, B, and C, you can permute these in cyclic order and it stays the same. So instead of having the psi dagger at the end, I could put it in front. That would be fine. So when you want to find the expectation value of an observable, you do this. Trace of psi dagger, operator psi. And that's consistent with what we had been doing earlier. As far as the Hamiltonian is concerned, well, it's still the same Hamiltonian. You see, and from this Hamiltonian, if you want to know how the wave function evolves, it is according to this Hamiltonian, but the matrix that describes this evolution is e to the power minus h. So remember, the density matrix came from e to the power minus h, whereas the matrix that transforms the wave function in time, that is e to the power minus ih. So there is a minor I here. That's the difference. Okay? And this you could compare with the classical transition matrix, which describes the evolution of probabilities, whereas the quantum one describes the evolution of wave functions. Now, when describing the evolution of probabilities, of course, probabilities have the property that when you add up all the components, it must be 1. And so to ensure that the probability stays normalized, this transition matrix has the property that every column must add up to 1. See, this is what we discussed in week 3. So that's called a stochastic matrix. With the quantum, of course, the size don't add up to 1. What adds up to 1 is the sum of the squares, which can be written as in this form. It's like psi 1 star psi 1 plus psi 2 star psi 2 all the way up to psi n star psi n. All of them must add up to 1, which means that psi dagger psi should be equal to 1. Remember, psi dagger is n by 1, psi dagger is 1 by n. So when you multiply the two, you get 1 by 1. And that's a number, and that's 1. And note the distinction with the density matrix, which was psi dagger, where you took n by 1 and multiply by 1 by n, and so what you get is a n by n matrix. See, but by reversing the order, you just get a single number, which must be 1. And what you can show is that in order to ensure that the transition matrix, or this transformation, this U, must be unitary. Just as here the W must be a stochastic matrix, columns adding up to 1, here U must be a unitary matrix, which means U dagger is equal to U dagger U is equal to the identity matrix. Okay. Well, that kind of, I guess, with time to summarize, what we'll be doing this week then is we'll be talking about quantum gates, which work on isolated systems where the wave functions are gradually transformed in time. And this time axis, it's convenient to kind of draw it from right to left instead of left to right, because then you see you have a wave function here and you repeatedly multiply it with different U matrices one after the other. So that way, if you draw it in this direction with the time going to the left, then the process of multiplication kind of comes naturally. So we'll generally be drawing it this way. And the idea is that a quantum gate will let you transform the wave function from an initial state as you go along. And this is different from what we had been doing earlier, the adiabatic quantum computing, where we basically were thinking of a quantum system that was coming to equilibrium. And the solution you have to look for in the density matrix. You have to engineer it so that useful things were reflected in the density matrix. Going forward this week, we'll be talking in terms of what is called gated quantum computing. And here we'll be talking about how wave functions evolve in time. Right? And of course, once you have the wave functions, you can calculate the expectation values of any observable just like before. And so what we'll be doing next then is, in the next 3 lectures, talking of different types of quantum gates and how they're used to do useful things. Thank you.